This is a tutorial for the lift formula problems that are part of the handout that I gave you on the lift formula. The basic lift formula is this. Lift is equal to the coefficient of lift times the density ratio times velocity squared times the surface area of the wing divided by 295. The 295 is a constant so that the speed can be in knots and the air density can be in density ratio. The normal lift formula has density, air density in slugs per cubic feet and the velocity in feet per second. The first problem is just the lift formula straight up, where you're given coefficient of lift, density ratio, true airspeed, and wing area. And so it's just a matter really of putting in all the information and solving for lift. In this case, lift is equal to 12,667 pounds, just multiplying all of that out. This next problem involves finding a speed change if we change some other part of the lift formula. So what I've done here is written out the lift formula, and then I've crossed out everything that either isn't given or isn't needed. And what we're given is a speed and a wing related to a wing area, and then another wing area, and we want to come up with a new speed. So the relationship of velocity and surface area is given in the lift formula. So, and it's really this particular relationship where velocity squared times surface area is part of the formula. So we can use that relationship to find what we need. So now I have two conditions that have to be equal. And I've labeled them the velocity squared of condition 1, which is the original condition, stall speed of 78 knots at a wing area of 105 square feet. So the stall speed squared, the velocity squared of condition 1 times the surface area of condition 1 has to be equal to the velocity squared of condition 2 times the surface area of condition 2. And so the three knowns that I have are velocity condition 1, surface area condition 1, and surface area condition 2. So now what I don't know is the velocity for the second condition, which is what I want to know. So I don't know that velocity. So now I simply solve those, algebraically manipulate that, so that I have velocity, my unknown is on one side of the equal sign, and I can solve out for those values. Simplifying the equation, I can take the square root of both sides, and then the square root of a number squared is equal to the number itself, so that puts the velocities as whole numbers rather than squared numbers, so I can work with them in a formula. So I wind up with the formula. My second velocity, the one I want, is equal to the first velocity times the original surface area divided by the new surface area square root. So the square root of the original surface area divided by the new surface area times the original velocity gives me my new velocity. So I plug those values into the formula. And my new velocity is 68 knots. And that is consistent. If I go from a smaller wing area to a larger wing area, I would expect the stall speed to go down. And so we went from 78 knots to 68 knots. So that is consistent with what would be reasonable to expect out of the problem. Okay, for this problem, we're wanting to find a particular density ratio. So we set it up in the same way. The two unknowns that were the two parts of the lift formula that we need are density ratio and velocity. Again, we wind up with an original condition and a next condition. In the next condition, we have one unknown. So we have a formula that we can set up like this. The two knowns, well, with three knowns. The arrows, the green arrows are showing what we know, and then we algebraically solve that for density ratio of condition 2. So we're going to solve that formula for that unknown. So that's just algebraic manipulation of that for the unknown on one side of the equal sign. Plug in values. So density ratio is 1. So that goes right here, 1 in the original condition times velocity of the first condition squared divided by the velocity of the second condition squared. Or alternately, we can take the square root of the original velocity divided by second velocity. And we wind up with a density ratio of 0.64. And what altitude would that be? Well, looking at just a basic standard atmosphere chart, we see that density ratio falls someplace between 10 and 15,000 feet. This problem is, again, we started out with the basic lift formula, and what we're wanting to find is now coefficient of lift. So we algebraically solve the lift formula for the coefficient of lift. So just algebraically manipulate that lift formula so that we isolate coefficient of lift and plug in the values from the problem, and we get a coefficient of lift. Then required of 2.16. For problem 5, we have the same situation where we've got the lift is the lift formula. We cross out the parts that we don't need or aren't given, and solve for. And then we wind up with the two conditions. We wind up what we need is coefficient of lift and velocity squared, and we're looking for a velocity. And so we've got the first condition and the second condition. We solve that algebraically for our velocity. So velocity squared is equal to the coefficient of lift times velocity squared, both condition 1, divided by coefficient of lift condition 2. Simplify the formula. Or we can take the square root of both sides. And when we take the square root of both sides, we wind up with eliminating the squared and the velocities, but putting a square root over the coefficient of lift divided by coefficient of lift 2, coefficient of lift 1 divided by coefficient of lift 2. So that's our formula. We substitute the values in. So CL max of 1.3, changing the CL max to 2.6, get the square root of that, multiply that by the original velocity, and we get a new velocity of 37 knots. If you increase the CL max from 1.3 to 2.6, let's say by the deployment of flaps, you would take the stall speed from 53 knots to 37 knots. And that makes sense. If the coefficient of lift goes up, the speed would come down. That's logical. And that concludes the first 5 problems on the worksheet.